So in the previous modules, we worked out for finite regions of space that the total flux is equal to the double integral of the divergence of the vector field across all the tiny, tiny rectangular regions in which we divided that finite region of space. And I'll point you to a link to the video where we worked this out in detail. Now, this is called Gauss's theorem. We extended this and wrote this down in another form where instead of having to write this as a flux, which is something we can calculate, we wrote this in the form of a line integral along the boundaries of the finite region of space that we were looking. So for instance, if this is the finite region of space we're looking at, and the vector field exists at each of these points along the boundary, we take the normal component of this vector field along the length of this loop and integrate that to obtain an expression for the flux in terms of the closed loop integral of the vector or of the normal component of this vector field. So that's how we technically define the flux. So if I write it in this form, I can write this as the vector field dotted with the normal component, and perhaps we've divided this boundary into tiny segments of length dl. Integrate, so we integrate v dot n, the normal component, the unit normal, multiplied by the length of these tiny little segments, and then sum up all these contributions. So that's sort of what the net flux or the net flow outside of this region would be. And we found that this is equal to the double integral of the divergence, which we can work out from the interior of this region. So if in the interior of this region we have these tiny infinitesimal loops, we calculate the divergence for each of these loops, multiplied by the area of these infinitesimal loop, and sum all of them up together, we get the right-hand side of this expression. And in this form, what we have is called the fundamental theorem of divergence. Now, the reason, as we pointed out in the last video, is the reason this fundamental theorem is interesting is because it has this structure where what occurs in the bulk or the interior of the region is completely encapsulated, completely captured by what is happening along the boundary. So this is the boundary, and on the right hand side we have the interior. Now, if we do the same kind of an analysis, but this time, instead of looking at the normal components, we look at the tangential components. So perhaps we have this vector field. I'll maybe draw another vector. We have the vector field here, and we take its component along the tangent to the boundary. We'll discover that we can extend the idea of how we defined the circulation and related it to the curl of the vector field. We can extend, and we did this for infinitesimal regions. You'll find that we can extend this, and maybe I'll just write it down. The tiny amount of circulation, or the circulation along a tiny infinitesimal region, we found is equal to the curl of the vector field times the area. Right? And if we extend this logic and sum up all the contributions, all the circulation contributions coming from all the infinitesimal regions, we sum this up, we do a double summation on the right hand side, we'll find that the total circulation is the double integral of the curl of the vector field, for each of these tiny segments, multiplied by the area of those tiny segments. And if we sum all of them up, we end up obtaining this double integral. And in this form, what we have is called the Stokes theorem. And just like for the divergence, we can write this circulation in another form, which is we can calculate the circulation purely along the boundaries of the region. And in this case, all we have to do is we take the tangential component of the vector field, i.e., we dot the vector field with the unit tangent along each of the points along the boundary, multiplied by the tiny infinitesimal length along that boundary, integrated along the loop. And we find that the right-hand side will be equal to the curl of the vector field summed up over all these tiny infinitesimal regions, or in the limit that del A tends to 0, and it becomes dA. And we find that the right-hand side can be written as a double integral. So in this form, what we have is called the fundamental theorem of curls. So this is what we refer to as the fundamental theorem of curls. Now notice it again has the same structure what is happening in the interior, the information we obtain from calculating the curl of the vector field in the interior of the region is completely captured by the integral of the vector field along the boundaries. So in a nutshell, if I write down the three fundamental theorems for you again as a summary, we began with what is called the fundamental theorem of gradients, which has the following form. For a scalar field, we calculate its gradient dotted with the length of the loop that we're considering. So, or perhaps in this case, an open loop, say we are going from point A to point B along some path like this, right? So we have from A to B. And the result of this integral is the value of the function f, the scalar function, evaluated purely at the endpoints. So notice, something calculated along the entire length of the loop is given purely by the value at the endpoints, which is the boundaries for a loop, for a path, for a curve. So this is the fundamental theorem of gradients. Then we derive the fundamental theorem of divergence and look at the nature of that particular integral. What we have is we calculate the divergence across at the interior of the region, interior of a finite region, and relate it to the value of the vector field or the normal component of the vector field evaluated along the length of the loop. So again, we have something in the interior being related to something purely evaluated at the boundaries. So that's the fundamental theorem of divergence. And in the third case, we obtain what is called the fundamental theorem of curls, which is again, calculate the curl at each of the interior points and then relate it to the value of the vector fields purely at the boundary. And that's the fundamental theorem of curls. So this very interesting feature relating the interior to something that occurs at the boundaries is shared by all of these fundamental theorems. And that's why we refer to them as fundamental theorems. And by the way, this is also what happens if you have a function of one variable. And that's the fundamental theorem of calculus, which we know about, right? So hopefully this was interesting to you. As a quick exercise, I encourage you to try writing a form for each of these expressions for three-dimensional space. We focused our attention on 2 dimensions. Let's see if you're able to come up with something in 3 dimensions. Do comment, do like, do subscribe if you're liking this content and would like for us to make more of these contents for you. Please provide your suggestions. Do visit www.dsigma.in for more in-depth details. And if you especially want to work out on some worked out problems, or if you want to have a one-to-one session with me. Thanks for watching. See you soon again.